Okay, so there's one more example here I have. Just create another geometry node. In this one, I didn't really talk about particles that much, although like they're really fun to work with. So we're going to make an example that starts off with a particle system and then build some more things on top if we have time. Particle systems are surprisingly easy in Houdini. They're like very straightforward. They're a bit the same as the particle sop in TouchDesigner. So it works in the same way that you need something to scatter the particles on before they start moving along. So for example, if we drop, say, a circle, for example, we could, if we add a transform node under this, connect them, something we haven't really seen, I mean, very briefly, if you $FF points, just $FF, at every frame, it's going to start rotating. Right, I mean, that's very basic, but it just gets the floating value of each frame and adds it to the rotation of the circle. So for example, if we copy this and put it on each axis, and then you hit the up arrow key, you get this very basic rotation effect. We're just using that to sort of make the spawning a bit more interesting. If we then drop a pop network, which is basically, it's a dynamics, the pop network is actually a DOP network, and the DOP networks are the dynamic operators. So that's where you run particle simulations, fluids, smoke, or vellum simulations as well. You get a lot of the dynamics running in there. So we'll connect the circle to the pop network, enable that, and if we jump in, okay, so we have a few things here from the grind up. So we have the output, which is just the output of the simulation. We have a solver here, which is a pop solver, which is basically a particle solver. We have a pop object, which is where the simulation actually lives. Or not really, but that's like what we get. The result of the simulation is on the pop object. And then we have the pop source. And if we look at the pop source and check the parameters, we have a lot of stuff here. We have the source, the birth, attributes, stream bindings, lots of stuff. The source is basically the geometry that we fed in to the solver here. In the popnet, sorry, that's the source here. In this case, we're using, if you go to geometry source, you can either, use first context, second, third, fourth context geometry, which just corresponds to those here. If we, connected this into the third one and used third context geometry, then, we would get that source again, but that's not what we want. Put it back on the first. So we're using first context geometry. We're using the geometry that's coming into the first node of the pop solver. And then you have different emission types. So either you scatter onto the surface, which we have here, or you scatter, you use the points, which are the points of the circle that we created here. If you create more points on your circle, you get more points on your popnet. Yeah. So if you press the up arrow key to start your timeline, you get this animation here, which is at each frame, it just like spawns some particles on the points of the circle. But because we have a transformation on it, those points change in space, and then when we get to the pop network, it follows that animation, but we don't yet have any animation happening on the particles themselves. One way of doing this, I mean, very simple, is we saw that earlier when we used the Vellum solver. Add a pop wind, and you just add it here after your source, your pop source. So basically, this thing here is where you can start adding all your particle behaviors. You wire them into this one, it gets fed into the solver, and then you get the output for it. If you run again, nothing happens, because we basically left everything by default, and there is nothing happening here. So you want to raise the amplitude to any number above 0, and you start to get a noise wind added to your particles. And then if we run the simulation again, we get this very simple effect. There we're using the emission type. If we go back to the pop source of points, so it's only spawning new particles on the points from our geometry. If we use all points and run the simulation again, it's, sorry, scatter onto surface, wrong one. There it's going to scatter them on the surface of the geometry you've just brought in, and then we get more of them, a bit nicer effect. And you have also, sorry, with scene points, and you have this one here, which is all geometry. And instead of actually creating particles, it's just going to deform the geometry itself and recreate, like respawn the geometry itself at each frame, and you get something different. But you know, in some, it's just in some cases. For example, if we go back to what we had earlier, like the open arc, which we used in the previous lane growth example, and we use that, then you know, we start to get this sort of effect. We don't have that many divisions. Anyway, so these are just like very basic different things you can do with the pop networks. So we'll go back to, I guess we'll just use points. And just one sec. Okay, so we've reset the simulation and we're just spawning around the circle. We're just spawning a bunch of new points every time. We can maybe increase the number of points on the circle, and then when we run the simulation, we'll get more, a bit like more denser distribution. There's something else we can add. There are many different pop nodes. So the particle nodes are like prefixed with pop, and there's a lot of them. For example, pop attract here, which attracts all your particles to a certain location. So a goal, if we run this again, they're all being attracted by, you know, the goal, which is 0, 0, 0. And if you go to the force tab here, you get the force scale. You can scale the attraction if you run it again. We've just changed the scale from 1 to 10, so they're being attracted much, much harder. In this case, we can add a negative scale, and then instead of being attracted to that point, your points will be repelled from, your particles will be repelled from the attract we've just had. So delete that, we don't need it. Okay, so to move on then, in the pop wind, you can, as we saw earlier, you can, you can add noise to the wind. It's just, again, like sort of a flow field for the particles to move in. There's a lot of parameters here you can play around with, like roughness, turbulence. Again, very similar to the stuff you see in TouchDesigner. There's also wind velocity, which just basically applies like a constant force in a certain direction. So I'm adding 1 to the Z wind velocity, which is going to push the particles forward. Now it's pushing them forward along the Z-axis. If I was to remove the noise and run it again, they would just all move forward. So pretty simple stuff, but pretty cool. Another one we can look at quickly is like pop axis force, which creates a sphere. You see here, like there's a red sphere and there's a lane in it, which is basically like the axis along which you're adding a force. If we up the radius and the height by going to pop axis force parameters, radius height, make this bigger and rerun the simulation, they're now going to be, I probably need to increase the orbit speed. If you go on the pop axis force on the second tab, you have the orbit speed. It's like basically like the speed at which they go to orbit around this axis, that's being visualized by this lane there. You start adding stuff. I mean, there's a lot of different stuff with the pops. Like there's, you can follow curves. There's a lot of stuff you can do, and they're like mostly like very easy to use and very intuitive. So you can get like a lot of particle effects up and running pretty quickly, and there's a lot of stuff that can be done. But what's interesting is that you can then use those particles either here, we just have this particle simulation, or you can use those particles for something else. You can use them to, copy spheres or geometry onto them or anything else, basically. You can use, they're just points in space and they can be used for any various number of effects. One thing that's there again, like made super simple in Houdini is this like very famous, like the plexus effect. I mean, if you were doing that in TouchDesigner, you have to start using geometry shaders to create, polygons between particles if they're at a certain distance from each other. It gets a bit more advanced. Like there's not really that much in TouchDesigner to make the effect from scratch. If we use the connect adjacent pieces here, it has like the connection type. Basically, it's going to connect different pieces together based on a search radius and a number of points it can search to. So in this case, we're going to have points. So if we drop down adjacent points, it's going to look through all of our particles, and for each one of them, it's going to connect to the closest points it can find. Within the search radius that we have here, you'll notice I've not connected it yet. Because like if you have a lot of particles, it can get pretty slow there again. I usually always reduce the max search points here before I connect them, just to avoid searching through like an insane number of particles. So it's going to search for a maximum of 10 points within a radius of 0.1. And if it finds neighbors that are close enough, it will connect them. So if we plug this in, connect them, there we go. We have like super simple. We've made this effect that if you run your simulation again or the animation, just up arrow key for the timeline, you get this, I mean, I think it's plexus is called, but you get this thing where you have this connection between different particles or points if they're within a certain distance from each other. See, for example, and then, start increasing the search distance. You get this pretty cool effect. So one thing that's quite good is if you drop a fuse node, you connect it straight after your popnet and then back into your connect adjacent pieces. Highlight the fuse node. What that does is it has this snap distance here. And that basically means that for every point in this particle cloud there that is, if 2 points are below this distance from each other, then they get snapped into 1 point. It allows you to sort of remove duplicates, basically. So you can increase this just a bit. And if you run a few frames in simulation, if you go on your .NET or your PopNet, sorry, and you select info, you have 15,000 points. If you go back to the fuse node, we have 7,375. We've basically, like, by increasing the snap distance, we've fused together or snapped together points that were pretty much overlapping. So you get a lot of, especially in the case of this connect adjacent pieces, you get a lot of duplicates because, you know, they're so close. So this sort of just reduces a bit the number of connections that are so close that we don't even see them. They're just like one on top of the other. All right, so we have this now, this connection of close points. If you let that run, you get this massive thing. I'm going to reduce very slightly this thing here. So if you've then gone into the connect adjacent pieces, depending on the search radius and the number of search points, we're going to get cases where we get points that have no close enough neighbors to connect them. In our case here, we can use the add sub, which, I mean, it does a lot of different things. It's a bit hybrid, but it has, if you connect it after the connect adjacent pieces, it has this pretty useful parameter, which is under the polygons tab, which is remove unused points. So basically, when you click this one or you check it, it looks in all those points, and if it detects points that are not part of polygons, so in our case, points that are not connected to anything else, then it deletes them. If you go back to connect adjacent pieces, we have, you know, on the outside here, we have points that are on their own. If you go back to the add point after we've checked remove unused points, then those points are gone. It just cleans it up a bit. And then, yeah, so there again, we have this simulation going. There's this pretty nice node, which is attribute blur. And there again, I mean, as we've seen from the start, each point, sorry, if we go back on the add node and to the geo spreadsheet, each point or vertex or what do you call it, primitive, has different parameters or attributes on them. It has P, X, Y, and Z because it has a position. And then if you're checking the geometry spreadsheet after after the PopNet, we have a ton of different attributes that were set by the PopNet, which are, you know, the age of the particle, is it dead? Does it have a previous? Does it, you know, velocities, IDs, you name it. There's a ton of different attributes on here. In this case, we're interested in the position attribute because what the attribute blur does is, it just the same way as you're blurring a texture with a top in TouchDesigner, it takes all the attributes from that geometry and blurs it. So if we connect the attribute blur and we want to blur the position to make some of them a bit closer and almost clumping together. Okay, so we highlight the attribute blur and uncheck pin border points. And you get, if you then increase the blurring iterations, you start to get this sort of web type of effect, which looks pretty nice. If we rerun from the start, rerun the simulation, and you compare that to the step just before, we had this very rigid sort of connection between the points, and then after the attribute blur, we get something that's starting to be a bit more organic. And that's like a really basic effect. And there again, you know, we could resample this if needed, but it's the sort of very simple effect of taking the, you know, connecting connecting close neighbors together and then blurring out their position to give them more of an organic feel. And there again, if you're doing this in TouchDesigner, it takes a lot more time. You have to start coding a lot of stuff. It's super simple in Houdini. It's like very straightforward. Yeah, there again, if any questions or anything, please feel free. What else? Yeah. So then there's we could use this structure here that we have to sort of create another type of growth. Here we have this like very stringy effect that grows with the particle system. If we use a time shift node connected here, highlighted, you'll see like there's a method by frame, then there's a frame field, and it's gray. If you select like right click and then delete channel, it goes black again. And basically it never changes value. It always has 112 in it, or the number of the frame at which you dropped the time shift. What this does is it just freezes everything before that node to that current frame. So if we freeze at frame 1, we have the very start of the simulation. If we freeze at frame 100, we have the state of the simulation 100 frames later. And that's super useful if you want to build something and then not have to resim it every time and just use that simulation at a specific frame, which is exactly what we're going to do here. What we're going to do is we're going to build some sort of growth through the network we have here, through the structure of points we have here. For that, we're going to take some starting points, put them in a group, and then another bunch of random points, and then put them in a different group and connect those groups together. It's a little bit abstract, but we're going to make this right now. So if we drop a point wrangle here and connect it, what we want is to get points that are close to the base of this structure here, so close to like where they were spawned from the simulation, and make them grow towards like the end to sort of expand out the way. So let's say we want like this part of like the 100 points here, like the 100 closest points to the center. You could say, for example, if take the point number. Okay, I'm going to read this and then we'll go through it. Oops. Okay, so there again, this point wrangle is just a small script, just like the Python scripts in TouchDesigner. It's a small script that just runs for each one of the points on our geometry. So we have a ton of points here, and every time this point wrangle is going to execute the same piece of code for each point. So what I've done is then I have PT_num, which we can visualize here, which corresponds to these numbers. So each point has a unique number. If the current point number is superior to the number in the number of points in my geometry minus 100, then we're going to do something with it. So this is just a number of the point we're iterating over. Endpoints is a function that gives you the number, the total number of points in our geometry. So it gives us, if we click on information here, 10,255. That's the number of points we have in this piece of geometry. The reason there's a 0 here is because we're using the geometry stream that's coming into the 0th input here. If I was working, let's say on this input here, I would have to use 1. I would have to do the user 1 here. That's basically just an argument that says I want the 0th input, or the first or second or third. Hope that makes sense. So basically that gives us a total number of points in the geometry here and minus 100. So if the number of my current point is, within the last 100 points in my geometry, I want to set that into a group. I want to say, this is a group of points that I want to make grow along my structure. So just the way we saw when we had the group nodes here and we selected, say, like, we make a group of my group and we say, for example, points, and we want all the points. That sort of implicitly sets the points into a group. The way you would do that with Vex, which is the language we're using here, you would say set point group. And again, we're working on geostream 0 because it's coming into 0th and like first input, so index 0. Then you have to give the group a name. So in this case, we'll just call it start. And then you give the index of the number which you want to put in that group. So in our case, it's the current point that we're iterating over. So if we're on point, if we were iterating over point 5812, then at this point, this would have value 5812, and it would put it in the point group called start. And then we have 1 because, we're setting it to 1. If you're putting it to 0, it removes it from the group. If you set to 1, it adds it to the group. So we have the last 100 points that have been added to a group. If we want to see that, we can use, for example, again, we saw that earlier, the blast node. Connect that. As soon as you highlight it, it deletes everything. But we want the start group that we just created here in the wrangle. And delete non-selected means you delete only the points that are not in the start group. And then we've isolated those that we just created. Yep. Don't need this. So this gives us the starting points of these structures, or like the growth that we were to make. We need endpoints. So for that, we can use the group range. We saw that earlier as well. Connect those here, and there again, change the group type to points because we're working on points. And say we want to select 1 of every 100 of them. And you see them there again, highlighted in orange. We see the points that have been selected, and group name, call it ends, for example, or anything you want. And here, if we drop a feigned shortest path node, it's going to connect a group of start nodes, starting points, to a group of ending points. So we connect this together, highlight it. You need to give it a few things. So we need the starting points, which we created at start. Endpoints, which we created in the ends group. And we want to go from any start to each end. I take the numbers off. And there is just basically created a bunch of connections between each of the ends we have and any of the starts. I'm just going to change one thing. Maybe if we lower the radius of the circle, yeah, we get something nicer. If we lower, so go back to the start and reduce the uniform scale of the circle we started with. We can rerun the sim. Yeah, it's a bit nicer. It creates like a structure that's got, it's more in one place. It's a bit nicer. Then fused some points. We looked at what they look like when we connect pieces. With the add sop, we removed unused points. And with the blur, we had this first effect. If we run this again, we have this sort of web sort of effect. And if we time shift this, we get a different point in time. If we scrub, it stays at that point. I'm going to use a different frame. That one's a bit nicer, I don't know. Okay, something like that. You may have to also, like, if you've changed the simulation above here, the time shift sort of tends to keep the previous sim it had in cache. So you may have to, like, just change that value here, and then you get the updated from your simulation. So then we've shifted this to always be on frame 100. With this small piece of code here, we've taken the last 100 points and we set them as a group with the name start to give it the starting points of our growth. We've then made a group range called ends over a point group type, and we've taken every 100. You could lower this, say every 50 points. So for every 50 points in the geometry, it adds it to the group ends, and then we have connected with faint short path between the starting points and the ending points. And this gives us this sort of tree thing here we have. And if you drop a carve node, not curve, carve, sorry, a carve node, we can actually grow these branches. Uncheck first you here, check second one, and there you have, if you play along with this, you can get you're growing those structures. What's quite nice is if you go back, for example, to the start of your timeline, and instead of using this here, which is a value between 0 and 1, you go from like 0% growth to 100% growth. If you select that and you say FF, so like the floating value of the frame, divided by $fend, essentially this means that we get the value of the current frame, so in this case 70, for example, and we divide it by the total number of frames, so fend, which corresponds to, if you go down your timeline to the right of it, you have this number 240, which is like the last frame. So we basically divide the current frame by the last frame, and it gives us a number between 0 and 1, and in terms of the percentage along the timeline. And then instead of having to use the parameter on the carve node, you can use your timeline, or you can just press the up arrow on your keyboard and actually play the timeline, and you get this growth that actually grows with your timeline. And there, as usual, if you go closer, highlight maybe the points, start seeing it's quite sparse. It's sharp angles again. If we drop a resample node after the carve, connect them, highlight it. There again, you've got more points, nicer curves. You can lower this, for example, get even more points along the curve, and treat the polygons as subdivision curves instead of having, that will get rid of, it gets rid of a lot of those, like hard edge angles. Lower this even more, and you get something smoother. I might actually add more points to my ends there, so selecting more endpoints, that way you get more structures. The less endpoints you get, of course, the less branches you get. So if we reduce that, we end up getting way more points and having something a bit nicer. Yeah, and that's pretty much it. Is it we could add after that, if smooth it. So the smooth node basically takes your geometry and tries to smooth it. It's pretty explicit with the name. Maybe smoothing. Yeah. So I often find that lowering the quality, the filter quality on the smooth node actually yields nicer results. I always think it gets like, it's sort of, yeah, I don't know. It feels like the smoothing is much stronger when you're using less quality on it, and you end up getting these sort of strands that are connected with each other. If you get rid of that, a different effect. You can also use what we used earlier on, like the attribute blur. There again, like not changing it, just keeping out on the positions and the uncheck pin border points. If you up the blurring iterations, and you get very close results to the smoothing. The smoothing actually looks nicer on this one. And yep, that's pretty much it. Again, the sweep node, as we saw before, that allows you to sweep geometry across your curves. Select the surface shape, select a round tube, and connect this here, and you get, okay, they're massive, but just reduce this. Very small radius, and you start, get something different. It's actually nicer like that, but yeah. And yeah, anyway. Yeah, so that's pretty much it. That's the last example I had. If there's any questions, as usual, feel free. And yeah, yes. So that's pretty much it. That's all the examples we had in the files, and I've rebuilt them, so some parameters may be a bit different, but it's pretty much the same stuff. So you can pick them apart, have fun with it, break them, anything.
Oh yeah, thank you so much, Dominique.
My pleasure.
Yeah. I think your explanation was pretty clear, and you always compare with the TouchDesigner, and you just show me the simple Houdini effect, but you show me tons of possibility on Houdini, and I think everyone really enjoyed your workshop. So
cool, thanks.
You guys have any questions? So if you have anything, then we're gonna wrap up soon. So feel free to post on the chat if you have any. Not sure if there's a question. Dominique, do you have anything to share? Your project or?
No, I mean, I have one thing, which is we're talking Houdini TouchDesigner. I mean, I'd had a few people approach me because I made this plugin for TouchDesigner, in which you could load Houdini scenes, and I think like a few people approached me asking how that worked, and I think like there again we go to the difference between both. I'd done this plugin that takes Houdini file and loads it into TouchDesigner, and you can whatever you change in Houdini live, then you get the result in TouchDesigner. But I think like. Yeah, it was fun to work with as a proof of concept, but the big thing I tell like every time I've been asked, like it's really hard to make them work together because one is so big and heavy. Like Houdini has a million things in it, and TouchDesigner is a bit more lightweight and super efficient for real-time stuff. So I think like talking Houdini and TouchDesigner is just a way of seeing how to get them to work together. And I think like getting them to work together in real time was like a really hard thing. So it's a bit of a different workflow and different results at the end, because working with Houdini, you don't really get that real-time simulation thing where you can just run and interact with it. It's a lot more like offline stuff.
I see. So we got some questions. Suna say, is there any plan to release Houdini engine that can be used with TouchDesigner? I think that one you already answered, right?
Yeah, I mean, I don't know if anyone else is making one. I don't know if Derivative have plans. I know that I tried last year. It works as a proof of concept, but I tried on one project using it as an installation project, and it was okay because it wasn't anything serious, and I was there. But it crashes a lot, and it's more like it's just really slow. It's really hard to get 60 frames per second when you're going from TouchDesigner to Houdini back to TouchDesigner. On the other hand, I mean, there is something I'm interested in, which is Houdini has the same, it can load different engines in. And I'm pretty interested in getting the tops. So like making a plugin for Houdini that you can load tops from TouchDesigner, because the top network from Houdini is really slow, and the one from TouchDesigner is like amazingly fast. So that would be like another area maybe to get some sort of real-time interaction, is to, they're again using the Houdini engine or the TouchDesigner engine to get them to work together. But I haven't really seen anyone else doing that, but I mean, maybe one day I'll start again, but at this point I have no plan for it. Sadly, I have no time. If I did, I would try, but I'll see.
Sounds great.